Hello folks, and welcome to Rational Science, the only site on the internet that does physics. Everybody else moves concepts around, and here we move objects. A rope is an object. A thread, I don't know if you can see that, it's an object. We only move objects. It's when you start moving concepts around like energy and mass and stretching the field and transferring the information. That's when it gets very scary. Some people even move the counter space. I usually move my beer from the counter before they move the counter space. Anyways, today we're going to talk about this subject, the God particle. Now, how's that for a subject matter? That's getting close to heaven, okay? The God particle. And this was proposed by this gentleman. His name is Peter Higgs. Won a Nobel for that. So that's the subject matter of today. If you have something better to do, well, then don't do it. Stick around, you might learn something. Okay, so what is this God particle? Well, it's the Higgs boson. I call it the Higgs boso. But it's okay, the Higgs boson, and it's a particle of mass. So before you can understand what the Higgs boson is and why this man, Higgs, won the Nobel Prize and why his name was used to give a name to this particle, you need to know a little bit about mass. What is mass? Okay. Now, we all know what mass is. I mean, everybody who went to high school, secondary school, right? We all learn it. Learn it in the first couple of weeks. Mass is the quantity of matter. Mass is either the quantity of matter or a measure of the quantity of matter of an object. Very simple, very straightforward. In fact, here you have the high school version by two prominent sites, so we have a little authority here, right? First one, mass. How much matter there is in something. Matter is anything you can touch physically. And the quantity of matter contained in an object by the Einstein's World of Physics. Open and shut case. That's what you learn in high school. And since 99% of the people never take physics, they never want to touch the subject ever again. That's what they come out of high school with, and this is what they repeat. And they say, yeah, it's the quantity of matter of an object. We're done. Not really. Not quite, okay? Here we have a little authority, okay? Just so we always put authority behind everything because I want to make sure that people believe in authority, okay? Here we have two very authoritative people. One is John Wheeler, Edwin Taylor. And Wheeler for sure is known by a lot of people out there. And they say nature does not offer us any concept as the amount of matter. History has struck down every proposal to define such a term. Even if we could count number of atoms or by any other counting method tried to evaluate amount of matter, that number would not equal mass. Now isn't that incredible? Here we have on the one hand, on the left, we have it's the quantity of matter. And on the right, these people say, no, that's not mass. That's a pretty inauspicious start for a theory that's going to propose a particle of mass. We don't have any idea what mass is. Keep in mind that Wheeler and Taylor, they're not telling you what mass is. They tell you what mass ain't. Okay, they say, no, quantity of matter, that's not mass. Not at the college level. Maybe at the high school level, for the peasants. Yeah, but not when you get to when you get to college. University level, mass starts getting quite weird. And it gets quite scary, really. And here you go to the Wikipedia and you'll find this. You'll find that mass is not the same thing as weight, okay? Even though mass is determined by measuring the object's weight. Okay? They're kind of weird because, mass is not weight, but we determine mass through weight. Great. And then they continue, in physical science, one may distinguish conceptually between at least 7 different aspects of mass, or 7 physical notions that invoke the concept mass. So it wasn't as easy as in high school, was it? I mean, in high school it was easy. Quantity of matter were done. And boy, as we studied mass and other things a little deeper, especially the mathematicians, these people who call themselves mathematical physicists, and that physicists is with quotations, the concept, the notion of mass has changed radically. And the question is, then what are they talking about when they say, for example, that a black hole has infinite mass or lots of mass? What does a black hole have? I mean, it'd be nice if they would define this mass thingy or point to it if it's a thing. so that we knew what they were talking about, right? And you know, one of the common notions people have is that you can take, for example, well, one thing that they did, take a hammer from the Earth. It weighs so much here on Earth. You can take it to the moon. It's got a different weight. And they claim that the weight changed, but the mass remained the same. Well, I got a problem with that because they, like they just said here, they're going to determine the mass by weighing. I mean, you know, it's not quantity of matter. We're not counting little atoms there. We're not counting units of mass. Okay, the way you determine mass is by weighing. In fact, for over 100 years, we had the Legrand in France, and that was the standard for the kilo, the Legrand kilo. And this was the 1 kilo, the standard. Every standard in the world was measured against that standard under certain conditions. Now they've got a new standard since the year 19, okay, 1 year ago. But the issue here is that, you know, the grand kilo has so much matter in it. And you can say, well, that's the mass. That's equivalent to 1 kilogram. But how did we determine that? Well, we put it on a scale and weighed it and say, there's your kilogram. We didn't count atoms. We didn't count units of mass. Counting is different than measuring. Okay, two different things. Counting, you get a number at the end of the counting. Whatever, 1 gazillion atoms, fine. So you put 1 gazillion. Measurement is something else. Measurement, weighing, you know, that's a totally different activity. And so you cannot compare measuring against counting. And it turns out that both mass and weight are determined through weighing, through measuring. Neither one is determined through counting. Okay, so that's important to make that distinction. So we have no difference between mass and weight until the mathematicians can figure out first what mass is, and then they can do something that separates mass from weight. Right now there is no distinction between mass and weight, as you know, so many people say, because the way we determine mass is through weight. We weigh it. Okay, so that's the first issue. And yeah, here you have the standard, you know, hammer and feather experiment done on the moon. And they say, well, these two have different masses, but they have the same weight. Why? Because essentially they fall to the Earth at the same time. Okay, and so obviously it was not. If you look at the structure of the feather against the hammer, and you could have put an elephant there as well, it wouldn't have mattered because they would have both fallen at the same time. The issue is whether they have different mass. And you would intuitively say, yeah, they have different mass. They've got different, like the hammer's got metal in it, you know, for example. And, you know, when you hold it in your hand, it weighs differently than the feather here on Earth, at least, right? Maybe not over there when it's floating in your hand, essentially. So they say it has different mass. Yeah, but what do you mean by that? I mean, do you determine it by feeling it, by weighing it? Is that how you determine mass? Well, that's weight. So how did you determine that the hammer has a different mass than the feather? if not by weight, okay? And people have a lot of answers, but they never hit that one on the nose. They never are able to answer that question. As hard as they try, I don't care how many years they study at the university, as of today, no one can tell you first what mass is, and second, the difference between mass and weight. And so there's the first homework for you, okay? Go and figure out in fine detail how you're going to determine that mass is different than weight. And please don't give me the party line because that's already failed. You got to invent something new. You got to come up with a new explanation of what mass is. First, the definition, and then how you determine that mass is different than weight, okay? And again, here you have it on Earth, just in case for those flat earthers who don't believe we went to the moon. Here you have, on the one hand, the metal and feather. They fall at the same time. Why? Because there's no air inside that box. Whereas when you put them side by side, you can see what's happening there, with and without air. Okay. Okay. With air, if the feather floats, and without air, the feather doesn't float. Okay. Okay. So that's the first issue. We have no idea what mass is, and we have no idea what the difference between mass and weight is. And so we're starting off on the wrong foot with this particle of mass. You know, it sounds more or less like, I don't know, the particle of love. I wish there was one. I throw it all the 18-year-old girls, you know, here, wham, wham, just bang them, hey, love me. Particle of love. And this is more or less the same thing. What is a particle of mass? Particle of a concept? It's like saying particle of weight. What sense does that make? And that's essentially what these people did, okay? Okay, an issue related to this is whether the photon has mass. Okay, and you'll see why, because this is what's going to lead to the Higgs boson. They're going to try to figure out because of this problem. Okay, so let's start here. What is the mass of a photon? Well, the physics fact frequently asked questions from the University of Riverside in California, and they have this. You can look it up. I've just chopped off a little bit of it. And says, does a photon have mass? After all, it has energy, and energy is equivalent to mass, right? E equals mc squared. Okay, there's a relation there between mass and energy. Straightforward, okay? And so they have this equation there. You can look it up in more detail. I'm just going to go through this quickly. And I'll look at that last one there. E squared, which is energy squared, is equal to P, which is momentum squared, C squared, velocity of light squared, plus, okay? The rest mass, m squared rest, sub rest, that's the rest mass, times velocity of light squared. So we have two situations which they analyze. They say if P is equal to 0, right, that little P in the red box there, P times C is 0. So that whole thing in the red frame goes to 0. And E is equal to the square root, because the square goes as square root on the other side. Okay, E equals square root of m squared, the rest mass squared, and a C to the fourth. Okay, and that you take the square root of that, and it's rest mass times velocity of light squared, which is the formula for Einstein's famous equation, E equals mc squared. The other scenario is, let's assume now that that the rest mass is 0. Okay, so we have now the m squared, what's in the green box, m squared sub rest, okay, that's the rest mass. If that goes to 0, right, then that whole thing in the green box goes to 0, okay, and E in that case is equal to momentum times the velocity of light squared. So no matter how you look at it, okay, you end up with something. Whether the rest mass is 0 or the momentum is 0, you end up with something, because the other factor is the one that will give you a greater than 0 value. Okay, that's what they're saying. Okay, I hope you understood that. It says when the particle photon is at rest, its relativistic mass has a minimum value called the rest mass. See, they don't say it has 0 value. It has a minimum value. They don't clarify that. I mean, what is minimum? Minimum is like 0 or like 1. It's just a minimum value, so they don't clarify that, okay, and very conveniently. As the particle is accelerated to ever higher speeds, its relativistic mass increases without limit. Okay, so after doing all this gibberish, this mathematical nonsense, does a photon have mass or not out there? That's what we want to know. I mean, are they playing here? Are they saying it's got both? Whenever we don't need the mass, we say it's got 0 mass. And whenever we do need it to have mass and we say it's got mass, we call it relativistic or rest mass or whatever. We just give it a name. You know, and they have these different masses. Again, Wikipedia says there's 7 different notions of mass, and you don't know what they're talking about after a while, because you don't know, the context changes. And so they say, oh no, here mass is something different. Here it's relativistic mass. Over there it's rest mass. And here we're talking about special relativity, and over there we're talking about general relativity, and over there about quantum mechanics. It's like every discipline, every branch of mathematical physics has a different value for the poor little photon. So we don't know how much it weighs. Does it weigh 0? Does it weigh greater than 0? We still don't know, okay? Okay, so here they continue with that a little bit, and here's just a pictorial version of that. Here the elephant's running at slow speed, so he's normal. But now, if he ran at great speeds, he increases in size. That's what these people are saying according to relativistic mass. Okay, elephant goes slow, he's the same size. He doesn't increase in size or whatever. It's when the elephant starts running fast, like close to the speed of light, that he grows in size. Somehow he picked up mass. Did he pick up more atoms? Is that what special relativity is saying? That when something travels at near speed of light, more atoms are piling up on them and they're growing like bigger and bigger and bigger? Certainly it's in opposition of length contraction, which happens also near the speed of light, where things get flattened out or shortened. So we get like, what do you mean that when we run at close to the speed of light, which is what special relativity claims, you have an increase in mass? What has increased? Are you talking about the weight? The weight against the scale? Is that what they're talking about? Are they confusing mass with weight? Keep that in mind. Okay. Anyways, I like the ending point from the physics fac at the University of Riverside. It says light is composed of photons. So we could ask if the photon has mass. Yeah, good question. Does it have mass? The answer is definitely no. Great. Could we stop there? No, we got to continue. The photon is a massless particle. Okay, great. According to theory, it has energy and momentum, but no mass. Okay, I thought energy was mass. And this is confirmed by experiment within blah, blah, blah. Okay, even before it was known that light is composed of photons, it was known that light carries momentum and will exert pressure on a surface. Yeah, it's known as weight. Okay, this is not evidence that it has mass, since momentum can't exist without mass. Okay, yeah. So we have a nothing, we have a spirit that's pushing up against the scale. It's got momentum, but it has no mass. That's what they're saying. Sometimes people like to say that the photon does have mass because a photon has energy. Okay, where h is Planck's constant and f is the free, okay. Energy, they say, is equivalent to mass according to Einstein's formula, okay. They also say that a photon has momentum, and momentum is related to mass by P equals mv. Okay, fine. What they are talking about is relativistic mass, an old concept that can cause confusion. No kidding. The photon has no rest mass, but does have relativistic mass. The use of relativistic mass makes it much easier to describe the mass changes that happen when light interacts with matter. Yeah, because they want to use that specifically for special relativity, where they accelerate something at close to the speed of light. Continuing here, the relativistic mass is a measure of energy of a particle, which changes with velocity. Again, sounds like they're confusing it with weight. Okay, because if you're going to move something, you're talking about different locations. Weight is location specific, not mass. They say that mass, what was the quantity of matter? Well, obviously, they're not using the notion of quantity of matter here at all. So by convention, relativistic mass is not usually called the mass of a particle in contemporary physics. So, at least semantically, it is wrong to say the photon has mass in this way. But you can say that the photon has relativistic mass if you really want to. Oh, great, so everybody can say whatever they want. In modern terminology, the mass of an object is its invariant mass, which is 0 for a photon. Okay, so I hope you understood all that and are ready to take the test. Does a photon have mass or doesn't it? I don't care about relativistic mass. I don't care about inertial mass or rest mass. I want to know if it has mass. No adjectives in front of it, please. Does it have mass or not? And they're going to say, well, which mass are you talking about? Again, they have 100 different types of masses. They have not defined the word mass, and they conveniently left it that way so that, you know, they can say whatever they want. Does it have mass? Yes, over here. And over there, well, no, it doesn't have mass. So what have we learned? They've covered all the bases by not defining the word mass. See, if you take Newton's equation, they run into trouble because it was mass divided by distance squared. Straightforward, quantity of matter. That's not the case, and they had to make amendments for to prop up special relativity, especially that one. Okay, so we started out on the wrong foot. We don't have a definition of the word mass. We don't know the difference between mass or weight. We can't tell the difference. They say some gibberish there, definitions, but they always weigh the mass. They always weigh to determine mass, so all we know is that it weighs differently. They have never were able to isolate the quantity of matter. Rest mass, the quantity of matter, what is that? Rest mass. The object is just standing still and you're counting how many atoms it has. You know, it has 1,000 atoms, just to make it simple, 1,000 hydrogen atoms. Okay, so it weighs 1,000 units of mass. That's not what they do. They weigh it and they say, well, we don't know how many atoms it has, it just weighs so much. Well, that's weight. And if you send it faster against the scale, which is what they do in special relativity, well, yeah, the scale is going to go, you know, it's just going to read a higher number. What have we learned? Okay, so we start on the wrong foot. No definition. We can't tell the difference between mass and weight. And then we have all these different relativistic and inertial and whatever masses out there that they invent every day. And then you don't know what a black hole has if it's full of mass. What is it full of? Okay, so what does this have to do with the Higgs? Well, here's where it starts. See? Here's where it starts. It turns out that I talked about it the other day a little bit, where they were trying to figure out where hydrogen was made. And they said, well, you know, inside the sun, you do not have enough pressure, heat, etc., to create a hydrogen atom. I mean, we can create the higher level atoms, the heavier atoms, elements, right, inside the sun, okay? So they have all these processes. But how about hydrogen, the building block that makes up everything else? So for that, they had to go to the beginning of the universe, to the beginning of what? Of the Big Bang. They said there you can find the pressures, the density, the temperature, the time. Okay, you've got pressure, every parameter that you need to create hydrogen, and that's what they were working on. Okay, and they said, okay, so here we go step by step. Quantum relativity physicists, quotations, sought the gut or the toe. What is the gut? Grand unified theory. At high energies, electromagnetic, weak, the W and Z bosons, right? And strong, the gluons, forces merge into a single force. That was shown by a couple guys who, three guys that won the Nobel Prize, I think 1979. And then what's the toe? The toe unites that plus gravity, especially the graviton. Okay, so they try to merge and create a single force that underlies all of them. That's the notion behind the toe and the gut, really. Okay, so what happened? At the Big Bang, the temperatures, the energy, density, time, all that, they can produce hydrogen atoms according to what we said the other day. Hans Bethe and some of these other fellows worked on that, and they said we got an idea of how hydrogen could have started at the Big Bang, right after the Big Bang. Not exactly at the Big Bang, but like a couple seconds later, actually fractions of a second. Okay, so what happened? Okay, so atoms and neutrons, they're made of quarks. Okay, and so where did the quark come from? Well, it came from a process they call the quark epoch. Okay, in this region, also in the fractions of a second, the quarks were created from there. They assembled first into protons and then into atoms. Okay, so that's the notion they have. It all comes down to the Big Bang and that process, the process that came right after the Big Bang. Microseconds after the Big Bang. Keep that in mind. Okay, but why do the W and Z's have mass, whereas the photon does not have mass? Again, they proceeded from the foundation that a photon does not have mass. And they forgot about special relativity. They say, well, that's another branch of science. We don't deal with that, you know. So yeah, the photon doesn't have mass. So again, you wonder, does it have mass or doesn't it have mass? Does it have momentum? Does it have energy? I don't care what it has. Does it have mass? That's all I want to know. A yes or a no would do, you know. It's a maybe. Okay, to this day, it's a maybe. Okay, so that was the starting point. They had to determine why or what caused matter to, especially the W's and Z's, which are particles which are inside the atom. Okay, so these particles are somewhere over there in the nucleus. You know, the nucleus used to be just protons and neutrons. Well, that's changed. You know, they put gluons in there. They put the weak and the W's and Z's in there as well. All these little beads, grains of sand between these monsters called quarks. Fine, okay. And when something happens, well, they shoot them out. Okay? And they call one the weak force, the strong force. The gluon are the ones that keep the quarks together, and so on. Okay, fine. So now we got to find out where the weak W and Z's came up with mass, whereas the photon, which was also apparently created at the Big Bang, or right after the Big Bang, microseconds after the Big Bang, how the photon ended up with no mass. These two ended up with mass, W's and Z's, and this one did not. And so this is the question they were investigating. Okay, so we got to keep that in mind, where all this starts. Okay, so here you see the evolution, so that you can see it in graphic mode. Okay, here's the moment of creation, time 0 at 10 minus 43 second of a second. Okay, so here we're talking about seconds all the way to the green part, almost. All that is less than a second. All that happened in microseconds. Like you see there, the quark epoch started at 10 minus 12 seconds. In other words, 1/trillionth of a second. Okay, so you can see this happened very fast. All this stuff. Okay, how did they figure all this out? Well, they calculated. Say, how much pressure do you need? How much time do you need? How much temperature do you need? How much mass or fields or whatever do you need? And they did all these calculations. That's how they came up with all these things. It's just a mathematical calculation. And they get Nobel Prizes for this, for saying, hey, I figured out, you know, when the atoms were created, it was created so many microseconds after the Big Bang. And this is what these people study, and this is what they get Nobel Prizes for, and this is what so-called theoretical physics is all about, calculating this nonsense. Okay? And of course, they never deal with the moment of creation, because creation is unknown. It's, you know, the latest they can go to, like 10 to the minus 42, and so on, of a second. And what happened before that, they don't know. After that, before that, I guess it's God. They can't explain the mechanism. They say it's unscientific because they can't prove it. They can't run an experiment. So go to philosophy and just do philosophizing all day long with them. So they have no explanation for the origin of matter. but they say we start at t plus 1, not at t equals 0. Okay, so that's important. They don't have an explanation for when it started, but they go through all these calculations. Okay, in order to understand what the Higgs is and how the Higgs enters this process of determining why the W's and Z's have mass and why the photon does not, you need to understand something known as symmetry breaking. Okay, very fancy term, scary for some people. I'll try to explain it as simple as possible. You got a Mexican hat, okay, and it's rounded at the top. You put a ball there. Well, it's not going to last long up there. But as long for that microsecond that it's still up there, you can see that the hat, but you look at it from one way or the other, it's essentially the same. Okay, so it's symmetric. Now, if the ball rolls down, which it will, it'll fall down, in this case, on either the left or the right. It doesn't matter. If it falls on the left or on the right, you can see that the hat is no longer symmetric. Okay, the left-hand side is not the same as the right-hand side. Okay, that's called symmetry breaking in a nutshell. How does that relate to the Higgs? Well, when we were at these gazillions of microseconds, okay, there was this field. God, he made the field, the Higgs field. There's a proposal that there was a field, and all these particles just crashed against the field, and some interacted and some did not. Okay, so you got some particles which interact, have friction, they scratch their elbows against the field, and others that whiz right through it for whatever reason. Okay, and so the more you interact with a field, the harder it is for you to get through this molasses. The other one goes through water and the other one goes through air, so one goes faster than the one through water, and the one through water goes faster than the one through molasses. And what happens, the more it takes for you to go through a denser, or the more interaction you have with this field, the more weight, the more mass you have. In other words, they turn mass into a dynamic concept. It's no longer counting how many particles you're made of. You can see that it's got to do with motion, with you pressing up against something. And we all understand that notion. Of course, we understand the notion. The question is, what does it have to do with mass out there? I mean, are we talking about quantity of matter, or are we talking about how much pressure you encounter as you move through a medium? These are two different kinds of notions of what mass is. And again, what they've done is they've turned mass into a dynamic concept. It depends on how much resistance, how much drag you encounter. Okay? And what happened was this symmetry breaking occurred then. And you say, huh, what's that? Well, what happened was that until then there was no resistance. But when they encountered the field, the Higgs field, it broke the symmetry. They couldn't return back to having no mass. Now some had mass and others did not. Okay? So it broke the symmetry. In other words, symmetry is when something doesn't change with what is called invariant. Okay? You continue onwards without any problem. If something changes, then it's no longer invariant. Now it's variable, not varied. Something changed. What changed was they acquired this resistance that these people call mass. Okay? So again, what is mass? It's the resistance to movement, not the quantity of matter. Okay? Because quantity of matter, we don't need to move the object at all. It's what you truly call rest mass. You have the apple, you count how many atoms it's got 1 billion atoms. That's the mass of the, assuming they're all hydrogen, right? That's the mass of the apple. That's got nothing to do with throwing the apple, whether through molasses, through water, through air, through some medium, and it encountering different resistances or different friction as it goes through these different media. Okay? So let's understand that first. So what was Higgs' contribution to this idea? Well, he created this mechanism, this C. He's one of the guys. There were several people working on it. He got the credit. I don't know why, but this is the notion. Okay, you have more particles, some particles interacting with this Higgs field, and the more it interacts, the slower it goes, well, the more mass it has. That's essentially what these people are saying. Okay, very simple concept, very irrational. Okay, very irrational, because what does this have to do with why you weigh more on the scale every morning after you've eaten? Are the particles pressing down on the scale more? I thought when you eat, you weigh more because you put more matter in your body. And these people are saying, well, yeah, that's the notion of high school. That's not mass at the university level. University level is a lot more complicated. I see. Yeah, no kidding. Okay. Here's because now we have to explain why. Why is there a difference between why doesn't the photon have mass and why do the other two have mass? So here we have the super duper scientific answer, which is several of them. First guy, and all these are authorities, okay? By the way, I took this out of only people who are physicists, who are really deep into all this math, etc., right? The Higgs does indeed interact with a photon. In other words, one guy says, yeah, there is interaction between the photon and the Higgs. Well, then why does it not have mass? And they say, and sometimes they'll tell you that the photon sometimes interacts with a Higgs field. So I guess the photon sometimes acquires mass and sometimes doesn't. I don't know. These people say whatever they want, and nobody even checks them. They just send them the check, their salaries, their grants, their Nobel Prizes, their medals, and nobody questions these things. The Higgs field is not electrically charged. Oh, that's one answer you'll find out there. And why not? Well, photons only interact with electromagnetic particles, such as protons and electrons. But it turns out they also interact with neutrons, because neutrons reflect photons as well, which are not electrically charged. And we know for a fact from general relativity that also they interact with gravitons, because relativity states that gravity bends light. So we haven't answered the question. Saying that the Higgs field only interacts with what is electrically charged does not tell us anything, because there are particles which, like neutrons and gravitons, which are not electrically charged, and they're alleged, the graviton, they're all alleged to have mass. So we haven't answered the question. But he got the Nobel anyways, okay? He got the little medal anyways. It's just a property of photons, similar to properties of other particles like electrons or protons having a charge which is their property. It just is so. It is so. God said, and it is good. That's it. There's no explanation. So he hasn't answered the question. He just came up with a mechanism, says, hey, I can explain the origin of mass. It's this river of molasses, and some particles can whiz through it and some cannot. And the ones that cannot have mass. That's all they said. They still can't tell you why the photon particle goes through that same molasses and doesn't have mass. It just whizzes right through. They just say it is, but they can't tell you why. What's got this particle got that all the others don't have. And the best answer for, if you're going to take the test, is just put all of the above. You're probably going to get it right anyways, It doesn't matter which one you answer, which A, B, C, or D. So you might as well just put all the above. So that's it. It doesn't get any better than that. But it doesn't stop there, because you wonder, well, why did this fellow get his Nobel Prize? I mean, yeah, anybody can come up with a theory and say, well, yeah, there's this river of the Higgs field out there, and everything that goes through it, well, different particles have different amounts of mass. Yeah, that's a theory, okay? There's a proposal. Why would this guy receive a pat in the back for this? Well, it turns out that, they went out there and they proved it. You need proof in mathematical physics, otherwise it doesn't hold. And so, let me get this. No, wrong one, sorry. Here's the LHC, and what they did was they accelerated particles, especially protons. In other words, they removed the electron from the hydrogen atom, and they claimed they accelerated these ions, and they made them crash against each other, okay? And after they did that, okay, so they were able to analyze the debris, you could say, okay? Okay, and so here's the debris, okay, more or less what they think it might look like in there. This is all obviously done with computers. It's not actual filming, okay? So let's keep that in mind. And okay, so they have, they watch this, they simulate it, and they say, okay, this is what we observed. And actually, it looks more like this, okay? Okay, so it looks like fireworks, collision, and little squiggly lines. Here they're straight, but they're really squiggly lines that come out of there, and they look at those squiggly lines and they say, oh, those are traces of particles escaping from ground zero. That's their notion of this. Okay, and by doing so, they were able to locate a little blip in the chart, and they said, hey, that's the Higgs. That's the one we predicted for the Higgs, and that's the right mass of the Higgs. which was 125 gigaelectron volts, the energy needed to accelerate a particle. And they have all these weird notions where, you know, you have a tiny particle, such as a quark, which weighs more than the gold atom that contains the quark. So you explain that. You know, I mean, that makes no sense whatsoever. Why do they have that? Because it's the amount of energy they need to accelerate something. And then they say, well, energy is mass, and so that's the mass of the particle. And so if you need more energy to accelerate a quark than you need to accelerate an atom, then the quark, which is part of the atom, weighs more than the atom. It's like the seed of the apple weighs more than the seed that contains the seed, weighs more than the apple that contains the seed. You figure it out. But this is what these people come up with. Okay, so here's what they gave Mr. Higgs the medal for. It says, for the theoretical discovery of a mechanism, the Brout-Englert Higgs mechanism. And they raised the first two names. They just left it as the Higgs mechanism today, you know, essentially. The other guys got the medal. Well, not Brout, he died, so they had to hurry up because these people are very old. They're close to 90, all of them. And so they say, well, before the next one dies, we better give them a medal because otherwise we'll lose the chance to give them a medal. And that's another thing with gold medals at the Nobel Olympics. And that's that, you know, they have to give it to the old folks before they die because they don't give medals to dead people, okay, at the Nobel. It's not, you don't give them retroactively, you know, like maybe the Iron Cross or something like that. No, it's got to be to a live person. And so these people were close to their 90s, said we better give them a medal before they die. One of them died. In fact, here I have this other fellow. If I can find him. Here he is. And his name is Francois Englert. And the other fellow was Brout, he died. And so they gave him what? What did they contribute? To our understanding of the origin of mass of subatomic particles, and which recently was confirmed. This was the key issue. Was confirmed through the discovery of the predicted fundamental particle by the ATLAS and CMS experiments at CERN Large Hadron Collider. Okay, so yeah, they came up with this notion, and that there's this river. And particles swimming through the river have different masses according to how much resistance they find. They can't answer the question of why the photon does not have mass. They don't have a definition for mass or the difference between mass and weight. And so what do we know today? Well, we know very little.